Welcome to this video. We will start with the problem of half wave rectifier and then we will discuss full wave rectifier. A half wave rectifier is used to supply 50-volt DC to a resistive load of 800 ohms. The diode has a resistance of 25 ohms. Calculate the AC voltage required. So the given data is the output DC voltage is 50, diode resistance is 25 ohms, load resistance is 800 ohms. We have to find out the maximum value of the AC voltage required. So what we will do is we will first find the DC voltage. That is DC voltage is given, but we can find the current from the DC voltage. So IDC into RL is VDC. But we know that IDC is, we can say, that is Im by pi. Im is Vm by Rf plus RL. That is into RL. So 50 is equal to 50 is the output voltage, that is into equal to Vm by pi into Rf plus RL into 800. So Vm will give you pi into 825 into 50 by 800. So it is just a substitution. We are just putting the value of IDC, that is Im by pi. But Im is maximum voltage is Vm by Rf plus RL. Then we will find the value of Vm. The next topic is full wave rectifier. So full wave rectifier, as the name says, it is a rectifier which converts both half cycles of AC into a DC current. So that is the positive and negative half cycles of the AC are converted into DC. So this can be achieved by two diodes working alternately. For the positive half cycle, one diode supplies current to the load, and for the negative half cycle, the other diode supplies current. The current is always in the same direction through the load. Therefore, a full wave rectifier utilizes both half cycles of input AC to produce the DC output. The following two circuits are commonly used for full wave rectification: center tap full wave rectifier and a full wave bridge rectifier. So you can see the diagram here. There are two diodes and a load resistor is connected at the center tap. So center tap full wave rectifier uses center tap circuit of the transformer. The load resistance is connected between the center tap and the junction of the two diodes where negative N type is connected. So in this circuit, the AC, the transformer, the secondary of the transformer is having two diodes, having the P type of the two diodes. So what happens is when during the positive half cycle of the AC, the secondary of the transformer, the point A will become positive during positive half cycle. At that time, the diode D1 is forward biased. As a result, the diode conducts current and the current flows through the load resistor in a clockwise direction. But during the negative half cycle, the diode D2 is forward biased. Therefore, there the D2 conducts current. Therefore, the current flows through D2 in the anti-clockwise direction through the load resistance RL. So anyhow, both the currents flow in the same direction in the RL. We can say there is a unidirectional current flowing through the load resistance RL. So peak inverse voltage. Suppose the maximum voltage across the secondary is Vm. The circuit at an instant secondary voltage reaches the maximum value in the positive direction. D1 is conducting while D2 is not conducting. Therefore, the whole of the secondary voltage appears across the non-conducting diode. So consequently, the peak inverse voltage is twice the maximum voltage across the half secondary winding. That is, therefore, the maximum voltage, the maximum inverse voltage is called as peak inverse voltage. So while the diode D2 is not conducting, what happens is the voltage at this lower half section is Vm and the remaining Vm is also acting across the secondary diode, second diode with D2. So that D2, which is in the reverse bias condition. So the maximum reverse bias voltage is what we call as peak inverse voltage. That is nothing but the total voltage across the secondary, which is twice the Vm, where Vm is the voltage across the half secondary. You see, what is the disadvantage? The disadvantage is that it is difficult to locate the center tap of the secondary winding. The DC output is small as each diode utilizes only one half of the transformer secondary voltage. The diodes used must have high peak inverse voltage. So the next topic is full wave bridge rectifier. In this circuit, even though it is a full wave rectifier, the center tap is not used. Rather, a different arrangement is used, having four diodes. So it is look like a square. The four arms of the square has a diode arranged in the what I say is in this way. That is, the two halves are in one direction. That is in anti-clockwise, and here is in clockwise direction. In the lower half is in low clockwise direction, and the load resistance is connected at diagonally one end, and the other end is grounded. So what happens is two diodes simultaneously conducts at a particular half cycle. So when during the positive half cycle of the AC, the point P is positive. Therefore, the diodes D1 and D3 are in forward bias. Therefore, the current flows through D1 and D3. And during the negative half cycle, the point Q is positive compared to the positive point P. Therefore, the diodes D2 and D4 are forward bias. Therefore, the current flows through D2 and D4. So let us see here. During the positive half cycle, the way of current flows is, see, to the D1, the current flows in this clockwise direction, and also the current flows in this direction, which is clockwise direction in the D3. During the negative half cycle, D2 current flows like this, and here the D4 current flows like this in this shown in the arrow. So now what will be the peak inverse voltage in this case? Now at a particular instant, the total reverse voltage is called peak inverse voltage. So suppose during positive half cycle, during positive half cycle of input AC, the end P of the secondary is positive and the end Q is negative. So under such conditions, the diodes D1 and D3 are forward bias. That can be replaced by wires. So as they are conducting, and then what will is remaining is the two diodes which are in the reverse bias condition. So the total voltage across the D2 and D4 are the same. That is equal to the total voltage across the secondary. So the peak inverse voltage is nothing but the maximum voltage across the secondary, that is Vm. But in the center tap transformer, we consider it as a 2 Vm. But here we are considering as a Vm. Now, what will be the frequency of the full wave rectifier? The frequency of the full wave rectifier is twice the input frequency, because in the input the positive half cycle comes every 360 degree, but here the positive half cycle comes every 180 degree. Therefore, the frequency is twice that of the input frequency. Now, coming to the efficiency, basically the DC output power by the AC input power is the efficiency. First of all, to find the DC output power, we find the current. That is, the current is AC current is V by RF plus RL. The instantaneous current is Vm by RF plus RL into sine theta. So what we will do is we have to find out the average using the integration method. But in this case, it will be 2 Im by pi as we already found in the half wave rectifier. So 2 Im by pi, that is for one half cycle, the two half cycles are there. So 2 Im by pi the whole square into RL is the output DC power. Then the AC input power is I square RMS into RF plus RL. But in this case, for a full wave rectifier, RMS is Im by root 2. So putting the value of IRMS, we will find the value of VAC and then I divide it, then I will get 0.812. That is 81.2% is the efficiency of a full wave rectifier. ഒരു problem ചെയ്യാം. ഒരു full wave rectifier uses two diodes. The Indian resistance of each diode is 20 ohms. Transformer RMS secondary voltage is 50 volt and the load resistance is 980 ohms. Find the mean load current. We are asked to find the mean load current, that is IDC, which is nothing but 2 Im by pi. So we have find Im. Im കണ്ടുപിടിക്കുന്നത് എങ്ങനെയാണ്? Vm current is current by voltage by current. Voltage by resistance. Voltage is 70.7 volt. എങ്ങനെ കിട്ടിയെന്ന് വെച്ച് കഴിഞ്ഞാൽ Vm is RMS into root 2 is Vm. So that will give you Im and then 2 M by pi will give you the load current or DC current. RMS value of load current is Im by root 2, which is Im is given, then I divide it by root 2, will get 50 milliamperes. Thus we come to the end of this video.